Hey class, let's look at another video of the trigonometric integrals, specifically ones that involve tangent and secant. In the first video, we concentrated on ones that involved sine and cosine. Just as a friendly reminder, some notes that you can also look on your Google Drive and get the extensive list of derivatives and any trig identities that you need. But a couple specific ones: the derivative of tangent x is secant squared x. Derivative of secant x is secant x tangent x. A good Pythagorean identity for this video is 1 plus tan squared equals secant squared. And if you subtract 1 on both sides, you get another identity. It's just in an alternate form. Tangent squared x equals secant squared x minus 1. Another handy derivative formula is the natural log derivative. Whatever trails it, in this example, or definition, natural log of u is the derivative of u over u itself, derivative over original. And then finally, the integral of secant x has an antiderivative of natural log secant x plus tangent x. And if the last slide, I will demonstrate why that's so. In our first example, we have the integral of tangent pi over 4x raised to the 6th power times secant pi over 4x raised to the 2nd power dx. Let's take our substitute as the tangent term. Take the derivative using chain rule. Divide both sides by pi over 4. And then go back to the original problem and trade out all the original terms for their substitution forms. And I've got to be careful to put 4 over pi in there because it's a multiple. It can come out front. There we go. The antiderivative of u to the 6th is 1/7 u to the 7. Plus c. And then once we trade our u back out for tangent of pi over 4, I'm going to go to the next slide. Let me recopy from the first. We had 4 over pi times 1/7 u to the 7th plus c. Multiplying those two coefficients, we get 4 over 7 pi. Tangent of pi over 4x, all raised to the 7th plus c. For our second example, we're going to look at secant of 4x to the 5th power times tangent of 4x dx. There's only one tangent to work with. If we use it as a substitute, its derivative is secant squared. But we can tell we've got way more secants than just 2 of them. Let's try secant as our substitute because its derivative is secant and just a single tangent along the ride. If it doesn't work, we can erase and start over. Using chain rule, divide both sides by 4. Okay, now let's go back to the original problem. What I'm going to do is before I do any substitutions, I'm going to break that secant term up. Specifically into 4 and 1. See how that kind of mimics the derivative of our substitute line? Making the substitutions, we get 1/4 u to the 4th du. The antiderivative of u to the 4th is 1/5 u to the 5th power plus c. That gives us 1/20th u to the 5th power plus c. And from our substitute, we can replace the u with secant of 4x. And remember, it's totally fine to put the 5 there. If you want to put the 5 outside the parentheses, that's just as good. No worries. And for our third example, we have the integral of tangent squared x over secant x dx. From the very first slide, we can rewrite tangent squared as secant squared minus 1. All over secant x. That's just using an identity to rewrite your terms. Splitting that into 2 terms with a common denominator, reducing secant squared x over secant x is just secant x. Secant is the reciprocal identity of cosine. Okay, so I'm going to recopy. Okay, here's where that very bottom integral on slide 1 at the very beginning of the video, secant has a really gnarly antiderivative. Natural log of secant x plus tangent x Cosine, it has a nice antiderivative of just sine. And then plus c, our constant of integration. Okay, so here's the reason that secant has that antiderivative of natural log of secant plus tangent. It's sort of a backwards way to show it. If we write a function as natural log of secant x plus tangent x, and using that front slide formula of derivative over original, we can take the derivative and it should come out as just plain old secant x. Let's check it out. Okay, so the formula for natural log's derivative is derivative over original. On the bottom, I'm just going to recopy secant x plus tan x. In the top, we have to put the derivative of those two trig functions. The derivative for secant is secant tangent. The derivative of tangent is secant squared. Factoring a secant x from the numerator, I'm going to go ahead and put that little dx. I didn't have room right above it, but I'll include it here. All over secant x plus tangent x. If you notice in the numerator in parentheses, we have tan x plus secant x. That matches the denominator. So we get a wonderful little cancellation there. And look at what's left over. Secant x dx. And that's why in every video, it seems like every video, I remind you that when you take an antiderivative, if you're not 100% sure that you got it right, take the derivative of what you wrote down, and it has to come right back out to what's before it. So we did the derivative and come out with secant. If you were to do the antiderivative of secant, it's got to come back out to that original function. Hope this helps.